your second video for 7.2 Antidifferentiation by Substitution. And this is picking up with example 6. We are evaluating the integral of the cotangent of 7 of x dx. Now, this is one that will teach you a little bit of a trick because it might not be as straightforward to figure out what your u is supposed to be here. Because cotangent on its own, we don't have anything whose derivative gives us just a cotangent by itself. But what you need to remember is that cotangent is cosine divided by sine. So this is the cosine of 7x divided by the sine of 7x, and then we have the dx. And if you rewrite this as this ratio, it becomes a lot clearer what we need to do in order to figure out what's going to be our u. So given your choice, if you have a fraction and you have a trig function in the top and a trig function in the bottom, typically your u value is going to be whatever is in the denominator. Because if I were to let my u be the cosine, I end up with a du in the denominator, and that just doesn't work. You need to have your du be either in the top of the fraction or no fraction at all. So again, when given the choice, you always want to let your u be whatever trig function is in the denominator. Now you may have to make some other adjustments, and you'll see that whenever we look at example 7, because we're going to look at some other properties and things of trig functions that you may come across. I have not seen these show up in the AP exam, but it is something that I do want to introduce to you guys so that you can work with them if you do see them in the future. So u is equal to sine of 7x, du is going to be 7 cosine of 7x dx, because it would be cosine of 7x and then times the derivative of 7x, which is 7, so I can put that 7 out in front. And again, I have the cosine of 7x dx in the top here. So I have that up here in the top, but I don't have the 7, so I need to move that 7 over. So this is going to be 1/7 du is equal to cosine of 7x dx. Your u then is going to be the 7x that we have at the bottom. So the 1/7 du, that's going to take the place of what's highlighted in blue. So this is going to be the integral of 1/7, and I will be pulling that out. I have a u on the bottom and then a du on the top. So this is really 1/7 times the integral of 1 over u du. So when we go to take the antiderivative, this should look familiar because 1 over u is one of those properties, one of those formulas that you have on the antidifferentiation page. This is going to be 1/7 times the natural log of u. It is important that you put the absolute value around that because this will account for u being positive, u being negative. So it is essential that you have that. And then again, we have our plus c. Once you put that in there, the only thing left to do then is substitute in for the u value. So this is going to be 1/7 natural log of the absolute value of sine of 7x and then plus c. Our next example actually is 3 different examples. Each one has their own unique quality about it, and we're going to be using a couple of different properties as we go through this. There is a page, remember, in the back of your textbook, I think it's around page 570, it might be like 573, that does go through some of your trig identities. So if you're not completely up to date on those, it may be a good idea to at least reference that section whenever you're working on some of these questions in your homework. So the first one is the integral of 1 over cosine squared of 2x and then dx. Of course, they have the dx on the top, but we could very easily put it off to the side. So cosine is 1 over secant, which means 1 over cosine is going to be secant. So this is really secant squared of 2x dx, which makes this a little bit easier to work with. Now we do know that the antiderivative of secant squared is tangent, but the 2x may pose a problem. So I'm going to go through the u process here, but I'm just going to let u be the 2x. I can't let it be the secant because I don't have the derivative of secant, which is secant tangent, in my problem. So I want to keep this as simple as possible because, again, I do know how to take the antiderivative of secant squared. Du is going to be 2 dx. So half du is going to equal dx. So really the only thing that I have to add into here, I'm going to change the 2x to a u, and I'm going to put that 1/2. And I'm actually going to pull the 1/2 out to begin with. I think we're to the point now where we can do that. And so then we have secant squared u du. So this is going to be half of tangent of u plus c. Scroll a little bit here. My u is 2x, so this is half of tangent of 2x plus c. So that one wasn't too bad. That was one of the easier questions that we're going to do in this section. For part B, I have cotangent squared. And again, there is no antiderivative formula that tells me what the antiderivative of cotangent squared is, nor is there anything I can take the derivative of and get a cotangent or a cotangent squared, but I can rewrite this using one of the formulas because cotangent squared is the same thing as cosecant squared minus 1. Put that 3 there. So this goes back to the sine squared plus cosine squared is 1. So cotangent squared is the same thing as cosecant squared minus 1. Notice I did have to put the 3x with, because that's my angle, so I did have to include that as well. And so this is going to be very similar to what we did in part A, where I'm going to let the u be the 3x. The du is the 3 dx, so I have a third du is my dx. And this one we are going to use the property rule where I'm going to take the integral of both parts because I am going to take the integral of the -1 in the course of my question. Now I can't, I am going to leave the 1/3 in with the question because you can't, well, you'll see what I mean whenever we go through your substitution for that. So I'm going to do this down here. I may need to scroll a little bit. This is going to be 1/3, or I'm sorry, I do need to pull out the 1/3. I'm getting confused about what I was doing there. My apologies. Because 1/3 du is equal to dx, so here is my dx. So I am going to change that to the 1/3 du. So I can pull the 1/3 out. In fact, I need to pull the 1/3 out. And then I have cosecant squared of u minus 1, and then du. So do my antiderivative. This is 1/3 times the antiderivative of cosecant squared is going to be a negative cotangent. So that is one where you have to keep in mind the negatives because the derivative of cotangent is negative cosecant squared. So if I need to get a positive cosecant squared, the cotangent had to be negative to begin with. And that's going to be minus u, and then plus c. Now here's where things get interesting because I do have to put in the 3x for both of the u's. So this is 1/3 times negative cotangent of 3x minus 3x. And then when you distribute that 1/3, you get negative 1/3 cotangent of 3x plus x plus c. So the 1/3 times the negative 3x, that actually simplifies to just an x. So something to keep in mind with that. I am going to have to scroll back up to do the next question, and the next one does involve a bit of rewriting in order to get to something where we can actually work with what we have. Okay, so cosine cubed dx of x dx. Cosine cubed, I can't let it equal cosine, because if you take the derivative of cosine, you're going to end up with a sine, and I don't have a sine, and I can't let it equal the whole cosine to the third power, because that would be 3 cosine squared. But I am going to break this up a little bit. So cosine cubed is the same thing as cosine squared times cosine. And then along the same lines, because again I said that the derivative of cosine is sine, is negative sine, and the derivative of sine is cosine. If I can change one of these to be something with a sine, then it would I would be able to actually go through and do something with this question. Well, the cosine squared is the key there. Kind of like what we did in part B, where I changed cotangent into cosecant squared minus 1. I can change cosine squared into 1 minus sine squared. So that's using the sine squared plus cosine squared is equal to 1. So if you were solving for cosine squared, you would subtract the sine squared. And by doing that substitution then, I can let u equal the sine, because then the derivative is merely a cosine. So if your derivative is cosine, I have a cosine of x dx in my question. It actually simplifies this quite nicely. So this is going to become the integral of 1 minus, there's no more sign here because I let that equal my u. It is still going to be squared though. So 1 minus u squared times, du. Now I can do my antiderivative, which is going to be u minus 1/3 u to the third power plus c. And then all we have to do is plug back in our u. So this is going to be sine of x minus 1/3 sine cubed of x, so sine to the third of x, and then plus c. Again, these ones do get a little bit tricky, so I wouldn't worry if you're hung up on the trig rules. It is helpful to know what your u is supposed to be. And again, you can always use the back of the book, the page 573 area, in order to get some of those relationships. The last thing we're going to look at is using the substitution method with definite integrals. So this is where, to avoid the resubstitution at the end, if you change the bounds to be in terms of u instead of in terms of x, you can actually save yourself some work. This only works if you do have bounds for a and b, so that's the numbers on the bottom and top of your integral like you have here. So we have the integral from 0 to pi over 3 of tangent of x times secant squared of x. Well, I'm going to let my u here be tangent because the derivative of tangent is secant squared dx, and that's what I actually already have in the problem. Now the other key here, though, is I need to find u of pi over 3, and I need to find u of 0. So that means instead of using the bounds as they are, you need to take those bound numbers and plug them into the u function to find the new bound. So u of pi over 3 would be tangent of pi over 3, and the tangent of pi over 3 is square root of 3. So for this integral, instead of having pi over 3 at the top, it's going to have a square root of 3 at the top. For u of 0, that's the tangent of 0, and the tangent of 0 is just 0, so that one actually does not change. And again, my tangent becomes the u, the secant squared x dx is going to become the du, and then I do my integral. So the integral of u is 1/2 u to the second power, and I'm evaluating that from 0 to square root of 3. So using that, the fundamental theorem of calculus, I plug in the top bound. So it's going to be 1/2 times the square root of 3 squared. And then I plug in the bottom bound, 1/2 times 0 squared. So when we go through and simplify that, square root of 3 squared is 3 times 1/2 is 3/2 minus 0 is simply 3/2. So notice I did not have to go back and replace the u with the tangent at the end and use the original bounds as long as I change the bounds to match whatever the u terms are rather than keeping them as the x terms. So that's a nice little shortcut when you're going through and solving questions. This will be our last problem in the 7.2. We're evaluating the integral from 0 to 1 of x over x squared minus 4 dx. So again, you have a fraction. You want the u to be the bottom of the fraction in most cases. And that also ends up being the bigger exponent of x. So when I take my derivative, I'm going to get 2x dx. Again, I don't have a 2, but I do have an x, so that's going to be 1/2 du is equal to x dx. And then I have to plug my bounds in. I have to find u of 1 and u of 0. Well, u of 1 is 1 squared minus 4. That's going to give me -3. U of 0, 0 squared minus 4, that's going to be -4. So this now becomes the integral from -4 to -3 of 1 over u du. So instead of putting the u on the top of the fraction, I'm going to put it off to the side. And I almost forgot the 1/2. The 1/2 I'm going to go ahead and pull out like I had there. I had half du. So I'm going to go ahead and pull that out. So now I do my antiderivative. So that's 1/2. The antiderivative of 1 over u is natural log of u, and that is going to have to be an absolute value or else this question will not work out. And then we're evaluating that from -4 to -3. So I'm going to plug in, and actually I'm going to pull the 1/2 out and deal with everything else first. So it's the natural log of absolute value of -3 minus the natural log absolute value of -4. So this is natural log 3 minus natural log 4. That's actually your, I believe it's called the quotient rule for logarithms. So you could, I guess you could technically leave your answer like this, although when you are subtracting two natural logs, that's actually the natural log of the fraction the first over the second. So it's 1/2 times the natural log of 3 over 4. But either answer would actually work. So again, that saved us from having to plug in the x squared minus 4 in the end of our question. It does make the work a little bit easier. You do have to use the absolute value with this one. It does not work without the absolute value. That's one of the reasons why the absolute value is actually in the formula for the antiderivative of 1 over u. Here's your homework. You've probably already seen this, especially if you've already looked in Schoology. So that wraps up 7.2, antidifferentiation by substitution. Please, please, please go back through and rewatch this if you're not sure, if it doesn't make sense. There are additional videos out there that you can watch if you need some more help with doing the antidifferentiation by substitution. This is almost guaranteed to show up in at least one or two places in the multiple choice. You might see this in the free response question as well, but especially if you're planning on continuing through calculus, this is something that will come up. So go back, watch this video, watch the first video, and reach out to me if you have any questions.